So next speaker is Thomas Sotiriou from Nottingham, and he's going to tell us about black hole scalarization. Please start, Thomas.
Thanks very much for the invitation. It brings back memories of the last course I was at Pushkin and St. Petersburg. Yeah, I'll talk about black hole scalarization. And since it's a modified gravity workshop, I'll be quite brief with a motivation. Yeah, so I'm sure you've all seen these kind of pictures before. You know, on the y-axis there is the curvature, on the x-axis there is gravitational potential, and you know these are various experiments and cataloged here basically according to the characteristic curvature, scale, and gravitational potential of the probe. And this kind of plot is usually used in talks to argue that gravitational waves, the Event Horizon telescope, and kind of current observations and future observations are probing unprecedented curvatures and gravitational potentials. And hence, we might actually find new physics with these experiments. This is, in principle, a correct argument, but there is a subtlety to it, of course. So, and this is that your ability to probe something new doesn't only depend on the curvatures and the potentials that you're probing, it also depends on the precision of your experiment. So you could have an experiment that probes lower curvatures, say, and potentials, but to a very high precision. You go in the context of a specific theory, you use this experiment to constrain, say, a coupling constant. Then you can go and perform an experiment at slightly larger curvatures or larger gravitational potentials. And you can actually get a weaker constraint if the second experiment is not as precise as the first one. And in fact, we have quite strong constraints from weak gravity on general relativity and deviations from it in the standard model. So if we want to claim that there's going to be some new physics or potentially discovered with current and future observations with gravitational waves or other probes of black holes and compact stars, there's some need to have theories or models that actually predict very strong deviations in the strong field regime while suppressing deviations very much in the weaker field. If you're a cosmologist, this is a game you've played before. You know, this is what cosmologists call screening. They just like it to work in the reverse way, right? You want to have models where new fields are very strongly suppressed in small scales, but they're allowed to introduce deviations in general relativity at very large scales, and hence be important in cosmology. So the question is really, could I do that? Could I really do it the other way around? Could I have theories where they look very, very much like they are in weak field, but in strong field, suddenly, you know, new fields appear? The oldest example in this game dates back to the 90s, so I'm going to walk you through it. It's a theory with just an extra scalar field. You can start here from what we call the Jordan frame action. So you have a scalar field, non-minimally coupled to gravity with a non-standard kinetic term, also a potential that is not particularly important here. And psi here denotes the matter fields. They only couple minimally to the metric. And then you can introduce, for convenience, a new metric, which is conformally related to the initial one. There's this conformal factor, and you also redefine the scalar field suitably. Then the conformal factor can be written in terms of the new scalar field and a function of it, a squared. This a depends on the choice of theory, so basically on the choice of omega. And then if I perform that redefinition, I go to the more convenient Einstein frame, where now I have just general relativity with a minimally coupled canonical scalar field with a redefined potential, and I've hidden all of the complications in the matter action, because obviously my matter field psi continue to couple minimally to the original metric g mu nu, which means if I rewrite this g mu nu in terms of the new metric, matter will now also couple to the scalar field. Now, if I forget for a moment the potential u, and I just vary this action, I get this equation here for the scalar, where on the right-hand side, T is the stress and the trace of the stress energy tensor of matter, and A is the function, the coupling, the conformal factor before in terms of the new scalar field, right? And prime its derivative. And if you inspect a little bit this equation, you see that, of course, if T is equal to 0, so the right-hand side works a bit like an effective potential for the scalar controlled by the matter. And if there is no matter, if T is equal to 0, you just have box phi equals 0, and phi equals constant solutions are admissible. These solutions will be solutions of general relativity. For phi equal constant, you can go and look at the modified Einstein's equations, and they'll tell you that it's just reduced to Einstein's equations. Now, if T is non-zero, generally the right-hand side would be sourcing the scalar field, and you can get non-trivial solutions for phi. But there is and hence, once phi is non-trivial, basically that will back react in the metric and you'll get a different configuration than in general relativity. But there is an interesting case when A cannot really vanish because it's a conformal factor between the two metrics, but when A prime vanishes for some constant value of the scalar, then this constant value, say phi 0, becomes an admissible solution of the system, even when matter is present. Then you plug that in the Einstein's equations as well, and you see that the theory admits all GR solutions so long as phi 0, phi is equal to phi 0. I mean, this is really not enough. Of course, you also want these solutions to be energetically preferable to kind of the solutions with non-trivial phi. And so, but as long as they are, the theory will behave exactly like general relativity around compact objects. Now, so the interesting point here pointed out in the 90s by Damour and Esposito-Farese is that basically such models exist where in low curvature, low density regimes, basically the GR configuration is preferable, and the solution describing, say, a star is exactly the GR solution. So you don't see any deviations from general relativity in the vicinity of the star, and you can really see that the scalar field is there. Whereas if you crank up the central density of the star and hence its compactness, eventually the GR configuration is no longer energetically preferable. The scalar field prefers to develop a non-trivial configuration, and suddenly, and quite sharply, in fact, deviations from general relativity appear. So how does that happen? Well, in this model by Damour and Esposito-Farese, A is chosen in the following way, where in fact A0 is either 0 or very, very small, for what I said to be true. And you can choose, for the sake of the argument, phi 0 to be 0 without sacrificing any generality. And if you look now at, say, a point in the spacetime, take the center of the star where you have the maximum density, and you see how the scalar field behaves, well, it really sees some sort of effective potential. If the density there is small enough, then this potential traps the scalar field very strongly, and it wants to be in that constant value. You start cracking up the central density and hence the compactness of the star, and the potential, this effective potential starts opening up. And what if you cross a certain threshold, it changes shape, becomes a little bit like a Mexican hat, and the scalar field develops what we call a tachyonic instability, and it wants to grow, and so it starts growing. This is a linear instability. Non-linear effects start becoming important, and it kind of rolls down the potential, and it finds itself in another stable configuration, right? And of course, that generates a whole profile for the scalar field, and now that your star has a non-trivial scalar configuration. The interesting, the very interesting point back then in the 90s about this paper is exactly what I said when I showed you that sketch of the various experiments, that back then people thought that weak field tests constrained scalar tensor theories very, very strongly. Binary pulses that started to be studied And people thought there is no point in using them, trying to constrain deviations from general relativity, because we have so strong constraint in the weak field that we're never going to get anything interesting from binary pulsar tests. That counted, paper counted as kind of a celebrated counterexample, where you had a theory that behaves exactly the same way as general relativity in the weak field regime, but shows large deviations for neutron stars. And in fact, this model is very, very severely constrained, so it motivated binary pulsar tests of general relativity. And in fact, it got really very constrained by now, almost ruled out by this test, unless you add a mass to the scalar field to suppress the profile of the scalar outside the star. Now, one important thing that I should mention is, for this to work, beta has to have to be sufficiently negative, the way it is defined here. If you flip the sign of beta, you get kind of the opposite behavior. You make the scalar ultra stable in the GR value, and the theory looks very much like GR. Now, this works for stars, but of course, if I go back in this equation here, if I set t equals 0, I just get box phi equals 0. So you already see that if instead of stars I wanted to consider black holes, this wouldn't really be a very interesting equation anymore. In fact, black holes in this type of theories would always be Kerr black holes, due to a theorem, by many, but most elegantly by Hawking. Which says that if box phi is equal to 0, and I'm in a black hole spacetime that is asymptotically flat and stationary, then the only solution to that equation is phi equals constant, right? So, and plugging in phi equals constant back to my equations, I know that these are Kerr black holes. And you can generalize this theory for self-interacting scalar fields as well. So this is going to give you the kind of well-known Damour-Esposito-Farese model of scalarization. Is going to give you scalarization of stars, but it's not going to give you scalarization of black holes. Now, this is not to say that obviously there aren't ways to evade that Noether theorem and endow black holes with some sort of scalar configuration or scalar cloud. I'm not going to go through this in full detail, but obviously Noether theorems depend on assumptions, and if you kind of violate these assumptions or relax them, you can get away with it. One very well-known example is, of course, that rotating black holes suffer from a super radiant instability, which can pump up the scalar field. If a black hole rotates fast enough, the scalar field can become a massive scalar field can become unstable, and then that could generate a scalar cloud. The way this circumvents the Noether theorem is that the scalar cloud is not infinitely long-lived, so it's not really a stationary configuration, but people have argued that it's long-lived enough to have astrophysical significance, right? Another one would be that you just don't have flat asymptotics. You feed the scalar field from infinity, or you have some matter around the black hole, and the matter scalarizes, and that scalarizes the black hole, and all of these are options that have been considered. But for today's talk, I really want to focus on whether you can have black holes which have their own scalarize on their own right, basically, and have their own charge, irrespective of any kind of effects, of any of the effects that I just mentioned. And it turns out that you can. So if you look at, let me start with this action here. This is again general relativity, minimally coupled scalar field, and now the scalar field couples not non-minimally to gravity, but not to the Ricci scalar, but to G, where G here is the Gauss-Bonnet invariant. So this is Kretschmann scalar, Riemann squared minus 4 times Ricci squared plus Ricci scalar squared. And I'm allowing the scalar to couple through some general function f to G. And if you start from this action, you get this equation here for the scalar field, and where f prime is the derivative, obviously, of f. And now, if you want this equation to admit phi equal constant solutions, then the f prime has to be such that for some value phi 0 it vanishes, right? So this is just a condition for GR solutions to be admissible. And you can actually prove, that if this condition is satisfied, and if that inequality that I've written here is satisfied as well, then these phi equal constant solutions are unique, right? Are the unique admissible solutions for black holes that are stationary and asymptotically flat. So this is basically a Noether theorem, very, very similar to the one by Hawking that I mentioned before, under these conditions. And if you inspect a little bit this inequality here, well, this is nothing more basically than requiring that the effective mass of the scalar perturbation, the effective mass square of the scalar perturbation is positive, right? So basically, if you start from this theory and you choose your function phi such that GR solutions are admissible, then they're going to be the only black hole solutions, provided that you satisfy this inequality here. If you don't, however, what you get is a scalar field around black hole spacetimes that can potentially have a negative mass square and hence a tachyonic instability, which is exactly what I talked about before in the Damour-Espósito, in the context of the Damour-Espósito-Farese model. So theories that don't satisfy this inequality could admit scalarization, basically, black hole scalarization. Now, this inequality has the function f, the second derivative of the function f, but it also has the Kreutzmann scalar. So, and we're talking about basically tachyonic instability around the GR solution. So I've written here the Kreutzmann scalar for the Kerr black hole, for a Kerr solution, where x here is the usual spin parameter multiplied by cos theta, which is just how it appears, the combination of which it appears. So, so chi. So when chi is 0, you just get Schwarzschild. And if you inspect a little bit this expression, you see that for chi equals 0, the Schwarzschild metric, G, the Gauss-Bonnet invariant, is actually sign definite in the theory. It's always positive, which means if you want to violate that inequality, you have to choose f prime phi 0 to be positive as well, and then you get a negative effective mass squared. Here I'm in curved spacetime, so a negative effective mass squared is really not enough to drive a tachyonic instability. You have to have a sufficiently negative mass, and for a given f prime of phi 0, which is given by your theory, basically by a coupling constant, in the value of phi 0, what controls the value of this effective mass is G itself. And G in this case is controlled by the mass of the black hole, which basically means if as I crank up the mass of the as I crank down the mass of the black hole, I make my black hole smaller, it becomes more compact, the curvature near the horizon grows, and that can make the effective mass of my scalar large enough to trigger that tachyonic instability, and then the Schwarzschild solution becomes unstable, and my black hole tends to develop scalar hair. And you can show in this case that there are scalarized solutions that come that appear, stationary scalarized solutions that appear as well. Sorry. Now, interestingly, if chi is not 0, so you actually have a Kerr black hole, you have a rotating black hole, G is no longer sign definite, which means you can choose phi double f double prime to be negative, which wouldn't give you scalarization for a Schwarzschild black hole. But if you crank up the spin large enough for any mass of the black hole, then the Gauss-Bonnet invariant turns to become negative near the horizon for a fastly enough rotating black hole, and it can be rotation that can trigger that tachyonic instability, and you can get what we call spin-induced scalarization, in which case only very rapidly rotating black holes carry scalar charge, whereas non-rotating black holes have no charge. And again, you can find stationary solutions that you expect to correspond to the endpoints of that instability. Now, are all of the solutions, it's obviously, it's not enough to show that I have an instability and then that for corresponding values there is a stationary solution. Ideally, I want to show that the instability indeed leads to dynamically to that solution. Otherwise, I'm not really sure. And indeed, you have to be careful with that. For instance, it has been shown that if I want to satisfy, take the spin-induced scalarization has been studied a lot less, so I'm going to focus for the rest in the one induced by the curvature and the mass. If I want to take the kind of the minimal model that exhibits scalarization, obviously all I have to do is pick this function f to be quadratic in phi and have a positive coupling constant in front of it, right? And it has been shown, in that case, I get scalarization. There are scalarized solutions, but these solutions have been shown to be unstable, radially unstable. Another potential, another phi that has been considered, another function f that has been considered is exponential of phi squared, which again gives you scalarization. In fact, at the same values because it's the same theory of the linearized limit, but it has stable solutions. This is easy to understand. This is, I've described to you as a tachyonic instability that is kind of quenched by nonlinear effects. So it's really the nonlinearity in the theory that determines the endpoint of that instability and hence the properties of the scalarized solution. And indeed, if I choose f to just be quadratic in phi, then the equation for the scalar is linear in phi. And once I start an instability in phi, the only kind of source of nonlinearity that could quench it would be back reaction. It would be phi growing, changing the metric, that changes the Kreutzmann scalar. And it turns out that this is not efficient enough to quench that instability. And the scalarized solutions that you find are not really the endpoints of that instability in that case. Whereas if you choose a coupling function that is nonlinear, you get a lot more nonlinearity. You amplify basically the nonlinear effects and you get better quenching and better properties for your solutions. And this nonlinearity doesn't have to come from a coupling function. It could just be a good old-fashioned phi to the 4 self-interaction, for instance, for the scalar that provides this nonlinearity. So indeed, what I'm showing you here is solutions for a theory that just has a simple quadratic coupling phi squared g with the right sign to lead to the tachyonic instability. But it has a self-interactions for the scalar in terms of a phi to the 4th potential. Right, and so what you see in the plot is basically mass versus scalar charge, and the little hats on the various quantities means that they've been rescaled with the coupling by the coupling constants that is sitting in front of the phi squared g term. In this way, whatever I'm showing you holds for any value of the coupling constants, basically for appropriate values of the mass and lambda, the phi to the 4th coupling. So what you see here is this dust line, vertical dust line, corresponds to the threshold mass below which the Schwarzschild solution is unstable. It's subject to that tachyonic instability. So all of this part, you can have Schwarzschild solution because it's unstable. Whereas the curves corresponds to stationary scalarized, static in this case, scalarized solutions that are asymptotically flat, right? For different values of lambda. So lambda equals 0 is the standard, is the theory without any self-interactions, just a small mass, bare mass. And what you see is that this curve tilts to the right. And this is quite important here because all of the unstable solutions are here, mass below the threshold. All of the scalarized solutions have mass above the threshold, which doesn't really seem good. If these solutions in that curve were the endpoint, of the instability, somehow they would have to increase their ADM mass and hence the energy of the configuration during that process, which doesn't seem likely, obviously. But if I start cranking up lambda, these curves start tilting slowly to the right, and you reach a stage where they lie on top of the unstable solutions in terms of mass, right? And indeed, you can check the radial stability, and then they become stable. So this is basically good indication that they are the endpoints of the scalarization instability. And that shows you the importance of the nonlinearity. Now, you can kind of go and find kind of minimal conditions for your theory to exhibit black hole scalarization or scalarization in general. In fact, you could ask the question, are there more models? There's a more exposed to Farese model, there's the coupling to G. Is there anything else I could do? Well, since at the linear level, this manifests as a tachyonic instability, you can just go in a large class of theories like for density and say, if I do linearized perturbations around a non-trivial background, what are all the terms that contribute quadratically in the action in perturbation theory, and which of them control a potential tachyonic instability? And I've written them here for you, and it's exactly what you'd expect, obviously. It's the standard mass term, the coupling that I showed with the Gauss-Bonnet invariant, a potential quadratic coupling with the Ricci scalar, and potentially a non-canonical kinetic term for your scalar field. And up to field redefinitions, these are the most general you can write. One question you could ask is, wait a second, where is the depth model? That was, that wasn't what you showed us in the first slide. Well, that term here, the phi square r, is at linear level is just a field redefinition as well from the Damour exposed to Farese model. And the non-trivial kinetic term, the non-canonical kinetic term, you can actually undo by this formal coupling and shift it, change the metric basically to cover so that you get this formal coupling to matter and you render that term canonical if you want. So really, the terms that really control the tachyonic instability are just the two ones that I said. The phi square r, that is really the depth model in this linearized form, and the phi square g. Now, when I started, I said that this term here, the coupling with the Ricci scalar, which is really the depth model, leads to neutron star scalarization, but it cannot lead to black hole scalarization. I discussed how this term here, the phi squared g, can lead to black hole scalarization. But in fact, since g is non-zero and gets large inside neutron stars, this term can also cause neutron star scalarization. So you can take both terms and go and study the threshold of that tachyonic instability, say in neutron stars, and both terms contribute to this. And this is an example of the plot. Since I'm running out of time, I'm not going to go through it in whole detail, but basically all of the shaded regions are unstable, and that wide island in the middle is a region where the neutron stars in GR are stable, and obviously this is for a specific equation of state and for a very heavy neutron star. If you change the mass of the neutron star and you lower it, that white region becomes larger, and in fact you can have an instability on the right-hand side of the plot where I'm pointing here. And the results change slightly if you change the equation of state. But if you put alpha equal to 0 and you're along the y-axis, then you recover the Damour exposed to Farese model. Conventionally, that leads you to scalarization for neutron stars of sufficiently negative beta. But in fact, for a very heavy star and for certain equations of state, and this is what you see here, you can actually get scalarization also for a positive beta for the center of the star, because the Ricci scalar changes sign in the center. But what I really want to you to take home here is that there is an island in the middle for basically mostly positive betas where neutron stars are stable and they won't scalarize in general relativity in these theories. So there are theories in which there are models in which only black holes will scalarize, and that has important observational consequences. Now, the last thing I want to say is that, as I said before, the phi square R coupling cannot really give you black hole scalarization, and it has mostly been ignored in the literature in this context. But it actually does contribute to the solutions in a very interesting way. So so obviously it doesn't contribute to the onset of the tachyonic instability, but it does provide back reaction that can quench that instability non-linearly, right? And it turns out that this is more effective than the one provided by the G coupling itself. So if I don't include any self-interactions, it turns out that this phi square R coupling can have a critical role on what will be the end state of my tachyonic instability and hence the properties of my scalarized black hole. And that's what I'm showing you here. So this plot is very, very similar to the one I showed for the phi to the fourth interactions. Beta equals 0 is the case where I only have the phi squared Z coupling, and of course I recover what I had before, a branch that is tilting to the right, and that suggests that these solutions are indeed stable. And as I start cranking up beta, then my branch starts tilting more, moving towards being more vertical and eventually tilting to the left. And for positive betas that are sufficiently large, I'm expecting to get nice stable solutions even without any self-interaction for my scalar field. Now, having this positive beta is kind of hitting many birds with one stone, because it allows you, based on the previous plot I showed you, to be in that region of the parameter space that neutron stars are not scalarized at all, and hence you wouldn't expect to get any constraints from binary pulses and so on and so forth. It allows you to stabilize your solutions, and on top of it, it actually gives you general relativity as a late-time cosmological attractor, and hence explains why you're going into that value of the potential of the scalar around which you develop that instability. Okay, so I'm gonna end here with some perspectives. So scalarization is basically kind of a form of screening that screens new physics at low curvatures and low gravitational potential. You can see it as such. It's basically, you can think of it as a linear instability that starts, it's a tachyonic nature that starts in a strong field, and then it quenches non-linearly and it leads to a non-trivial field configuration, right? And in this case, you can capture its onset purely through perturbation theory around some trivial solution where your scalar field sees some effective metric and some effective mass. This is kind of a useful way to determine kind of the minimal action that you can have to have this phenomenon. But of course, the details and the properties of scalarized solutions depend entirely on the non-linear terms that you add. So you can have a very wide variety of different scalarization models that lead to different properties for compact objects. People have considered generalizations to this kind of mechanism, vectorization, tensorization, basically how you could apply the same logic to vectors and scalars and kind of have this kind of phase transition basically in different fields. People have suggested that there might be different type of instabilities, tachyonic instabilities that are not related to gravity, or non-tachyonic instabilities that are again non-linearly quenched, and they happen in the strong field regime and then they're non-linearly quenched. And of course, there are also major challenges in these models. So one kind of fairly obvious one is that these terms, these couplings to curvature, they're going to become more and more important as I go to the early universe and the curvature of the universe grows. For all of this, for black hole scalarization to work, you need curvature. You need basically these terms to be important of curvatures of order kilometer, which means once the universe becomes of that size, these terms will be important, and you need to find ways to control them in the early universe. Also, not, as I said, kind of following the process of scalarization, or actually, or at least following the dynamics of theories that exhibit scalarization is an ongoing challenge, because obviously theories with this kind of non-minimal couplings are not easy to handle, and it's a question of whether they are well-posed theories, and this is also something under investigation. I will close with a statement that basically scalarization is not a theory. It's a little bit like inflation. It's really a mechanism that wants to become a theory, needs to be kind of embedded in a bigger theory to become a theory itself. And that's all. Thanks very much.
Okay, thank you very much. So question, Paolo, please.
I think Alexis was first. I just raised my hand.
Okay. Okay, so Alex, please.
Okay. Thank you, Thomas, for this very interesting talk. I have only a small comment just related to your short remark about cosmology, in the case of psi r twice squared coupling. So in this case, as far as I understand, I would like to attract your attention to the result about which I spoke in my talk in the other symposium. So it's I think its notation is just the case of psi twice squared r coupling with large psi. So in this case, we know from cosmology that the resulting scalar tensor model can be well approximated by the pure geometrical R plus F over R model. In particular, this is used to show that in the case of mixed Higgs R squared inflation, this is in fact a kind of R plus R squared inflation, and that's why I use in some sense opposite term instead of saying of scalarization. In this case, I said that we have a geometrization of a scalar.
Okay, thanks very much, Alexei, for that comment.
Okay. So, Paolo, please.
Yeah, hi Thomas, nice talk.
Hi, Paolo.
So I have a question related to the case or to the models in which also the scalarized solution is unstable. So what is your intuition? So what happens is, say, I start with a Schwarzschild black hole in that theory, which is unstable, and then toward which solution does it evolve? I mean, what happens?
Sorry, you're asking for the theories where the scalarized solution is shown to be radially unstable.
Right. Okay. So that it cannot be the end state.
Yeah, I mean, I think obviously this is intuition at this stage because you need to do a calculation, which I haven't done. But I mean, my intuition tells me that basically these solutions do not exist in the sense that the Schwarzschild is unstable, right? So you start to depart from it tachyonically. But if the other solution, if the ones that the stationary scalarized solution is radially unstable, obviously evolution will not take you to an unstable solution. So they're both unstable, and hence, in this sense, these models predict that there are no black holes beyond that threshold, basically, right? This is how I would interpret it. So if you were to drive basically the coupling to these values, then beyond the threshold of the so let me go back to my plot, maybe it will help to discuss this. So so we're talking basically, say, about that curve here, right? So basically below the threshold mass here, Schwarzschild is unstable, so Schwarzschild black holes do not exist. These solutions here, Schwarzschild is stable, so you're perfectly fine, right? And all of these solutions that lie along this curve exist mathematically, but are unstable themselves, so they're never going to form. So what I would expect is that in this theory, black holes are Schwarzschild up to the threshold, and then there are no black holes beyond that.
Do you mean that there is a sort of runaway behavior of the scalar field? That's what you mean?
Yeah. I mean, around the Schwarzschild solution, yeah, it would just be kind of an endless instability that you cannot control, right? That's what I would conjecture, basically. I mean, perhaps an important point here is that in general, in theories where the scalar couples to the Gauss-Bonnet invariant, even when you don't have scalarization and you always have hair, right? Like you know, e to the phi coupling and so on and so forth, coming from heterotic strings and so on and so forth. Black holes have tend to have a minimum mass, a minimum size as well. So it's not kind of entirely new that beyond a certain limit, you stop having black holes. Beyond a certain mass, you stop having black holes. It's kind of a generic feature of this theory.
And sorry, what will happen there? I mean, if I choose those couplings and, for example, study the collapse of this Scalar field of some other matter field, what should happen?
I mean, I think you're just not going to be able to do the calculation. I mean, in a sense that numerically you'll just see an instability and you'll lose control basically of the dynamics, right? But what happens in nature is probably what the theories are ruled out. I mean, at least if we observe black holes below that mass or something, it could also be that something that if you try to collapse below that mass, it will disperse or something like that, right? Physically, instead of collapsing to a black hole.
Okay, thanks.
Zakaria?
Yeah, so thank you very much for the nice talk. I have many questions. The first one, when you said cosmic evolution can lead to Scalar, what did you mean by that? The second one, it's about because you proved that if the cosmic scalar field is subdominant, so there is no problem for late-time cosmology. What about if this cosmic scalar hair is responsible for late-time cosmology and is the dominant one? So if there is any problem, because we know that there is a catastrophical instability for inflation, but what about the late-time acceleration? And the other one, when you have your model of most general scalar tensor, it's about Hurdinsky, right? So if we allow all the theory space, so that can we find like some theories that can lead also to late-time cosmology and at the same time can lead to scalarization? And can we go beyond Hurdinsky also to construct this scalarization also?
Yeah. Okay. So I'm going to start from the end. I don't know the answer to your last question. I don't know if there are any theories that exhibit black hole scalarization and also have a non-trivial cosmology. I mean, I'm not sure you have to. I'm not a fan of trying to kill many birds with one stone. I mean, you don't have to have one field that does everything for you. Scalarized black holes explains dark energy, explains dark matter, and so on and so forth. A fundamental theory might be more complicated than this and have various extra degrees of freedom. Now, and then for your previous two questions, let me go a step back. Basically, a fundamental question you could have in this kind of models, and already this discussion started with the Damouras-Poisson Farese model, is you have this kind of tachyonic instability around. You can show that you have this tachyonic instability around a specific value of the scalar field, phi 0, and that depends on the theory. But the point is, if cosmic evolution doesn't drive you around phi 0, then your solutions, everything will be scalarized. There's going to be a non-trivial scalar because only if you're at phi 0 do you get GR, or at least only if you're close enough to phi 0 do you get approximately GR, right? So a potential problem there is that if you kind of follow the evolution of the universe, if you kind of don't descalarize at some point, then the whole scalarization mechanism around compact objects becomes kind of irrelevant, and then the whole universe remains scalarized for the whole cosmic evolution, right? And in fact, that's why I made kind of a fuss about adding this beta positive term for the phi square R coupling. And so basically, in cosmic evolution, if this term becomes more important than the G coupling at low curvatures, obviously, and if beta is positive, then that drives you towards that value of phi 0 that you want in the late universe. So in the late universe, it tells you the universe has kind of descalarized compact objects, or actually any structure in the universe is sitting in a region with constant scalar that has the right value, and then only when locally curvature starts to grow again and these couplings become important, can you trigger that scalarization, right? So you need both of these things to happen at the same time to have physically relevant scalarization and not be scalarized throughout the evolution of the universe.
Okay, thank you. And what about, so the only coupling that can we have for scalarization is the coupling with curvature, like with the ghost boundary term. Can we generalize this? Or like, for example, if you go beyond Holinsky, like, can we have some other operators coupled or?
I mean, you know, these are the couplings. So what I've written here are basically the terms that will contribute to the onset of scalarization in the sense of tachyonic instability. But you can add any sorts of term here that you like, and they will all affect the structure of the final object, the endpoint of the instability. Because as I said, the onset is linear, the endpoint is determined non-linearly. So you can kind of play infinitely with different terms here and change the behavior of the final compact object and its properties, its stability, how much charge it will have, and so on and so forth. Yeah. So and you can go beyond Hordensky. You can do what you want in this respect.
And just one last point about screening mechanism. I didn't understand it. So we don't need the screening mechanism because these effects will become very large in strong regime. But these theories are endowed, for example, or embedded in Hordensky theories. And there are a lot of theories that have screening mechanism. So how can we see the screening near the black hole when we have this phenomena of scalarization?
Oh, the screening is reversed here, right? The black hole will have a small black hole will have hair, right? Whereas the sun, for instance, will not, because basically what happens is that when the curvature drops, the scalar field is kind of trapped in an effective potential, and it's very, very rapidly driven into the trivial constant configuration, right? Okay. I'm not sure if this was your question, but.
Thank you very much.
Okay. So, sorry, we don't have much time, so yeah, can I stop here? Okay, Thomas, thanks.
Sure.